Now we're going to talk about improper integrals with something called infinite discontinuities. And I don't mean that there's an infinite number of discontinuities. I mean the type of discontinuity is the infinite one, meaning that, just a quick example, we have like something that dips down to infinity and then maybe like comes back up. And we want to find, let's say, the area from here to here. We have to somehow traverse that discontinuity somehow. And then there's also the case where we have a discontinuity like this. We might have to check something like that. And this is what this video will be aimed to looking at. So time for the definition, right? Let's say, let me write it in blue since it's important, and I forgot I have to scroll this a bit down. Hopefully it won't be, okay, there we go. The first one is basically what happens when we have something where the endpoint for A, or an endpoint discontinuity, where it's not specifically defined at A, but we can kind of because it's an open interval at A. So what I want to do is basically see that AB f of x, how do we solve this problem? This is kind of in contrast to the infinite one. We have to do basically the same thing actually. It's not really in contrast, I mean similarly. I want to use a variable, I'll just use C. And notice that we're approaching A from the, not from the negative side. We're approaching A from the positive side because it's the lower limit. So because A is that part where the discontinuity can happen, we have to approach it from the right side. And it doesn't really make a huge difference in our calculation. It's just like this, right? And then we evaluate it very similarly to just how we do an integral, and then we evaluate the limit just like we do with any limit. And the other case is when you have when the lower limit's actually continuous but the upper limit is not, right? So we have a very similar case. Now in this case we basically do a very similar thing, right? We just go from A to B of f of x, but the way we solve it is very similar too. The limit as c approaches, and notice it's b from the minus or the left side because it's the upper limit. And then now it's just a to c of f of x dx, and that's the idea of infinite discontinuities. And then lastly there's that same one where they're kind of somewhere in the middle, right? Something in the middle. So I'm going to define something in the middle of the interval being discontinuous is a to c and c to b. This is u, or it's called the union, or how basically you have this section and this section. That's what this means. It's kind of like and, if you want to think of it like that. So how do we go ahead and try this one? Well, it's very similar to kind of like that infinite on both the bottom and the top. We just want to break it up into two parts. So if we want to go from A to B, we break it up into two parts. The limit as what is this? The B, I guess the limit as C, or sorry, not C, D, because we ran out of letters, goes to C from the left side of A to D f of x dx. Plus the limit, let me use a different variable, E. I probably don't want to use E because E is a number. F is the name of the function. Let's just use G. You can use any letter again. So now we want to approach G as G approaches C from the what? This is the positive direction of that same integral. Oops, now it's what is this? Now it's C, or G in this case, to B. Yes. Because if we just think about attaching all the parts together, we go from A to D, which is basically C, and G, which is basically C, to B. So in other words, A to C and C to B. Yeah, and the same idea works. We have this idea of convergence and divergence, where it's just like if it's a number, it converges. If it's infinity or negative infinity, it is a diverging one. So let's do some. And I'll also add, we don't really use the third one too much because you can just simply think of it as this part find the integral of this part using, I guess, rule 2, and then find the integral of this part using rule 1. So we don't really think of 3. It's kind of like a combination of 1 and 2 if you want to think of it like that. So here we go. So here we have a relatively simple looking one, right? The integral from 1 to 2 of 1 over x minus 2 dx. But what makes this a little bit more tricky is that there's a discontinuity at the endpoint, or the upper limit 2, right? If we plug in 2 there of the function right here, if we plug in 2 here, it's going to be something over 0. So that's the discontinuity I'm talking about. So we actually have to redefine it as the limit as b approaches 2 from which side? So it comes in from the left side, so it's the minus from the left side of the same integral, but just replace it with b. dx 1 minus 2, and we can evaluate this integral pretty easily because it's just a simple natural log x minus 2, and we evaluate it at 1 and b. So let's actually try doing this now. I can plug in the limit. Oops, I scrolled the screen too much a little bit. There we go. So we can evaluate this integral. It's the limit as b approaches 2 from the left side of natural log of b minus 2 minus the natural log of, what is this, 1 minus 2. What's the absolute value? So in other words, this is just the natural log of 1. So I'm going to actually just substitute this. This goes to 0. We're basically just focusing on the limit as b approaches 2 from the left side of the natural log of b minus 2. And what is this? Well, if we plug in, or if we kind of think about this, if we plug in 2, where do we go? The ln goes to 0, and if you know something about the regular ln function, oops, let me draw it a little bit better. So if this is the ln function, it looks something like this. Notice that if we approach the discontinuity part, or if we approach something that, if we approach 0, we go to negative infinity. Right? It's never going to reach that. It's never going to cross that y-axis. So if this approaches 0, that means it should approach negative infinity. In other words, we can say this integral diverges. And that's basically all the work you have to show. You have to basically show that you can evaluate the limit. I'll evaluate the integral first, then evaluate the limit, and show that it is an infinity one or a negative infinity, and just state diverges. If it's a number, then you know it converges. You can state it converges and write what it converges to. So like, for example, like 0, maybe it converges to 0. So let's look at another example. So here we have our next example, integral from 0 to 3 of the function 1 over the quantity x minus 1 raised to the 2 over 3 power. And notice that the discontinuity here happens at the interior point, so there's a discontinuity at x equals 1, right? Because if you plug in 1 to this function, it's something over 0, 1 over 0 in this case, and you can't have that happen, so we actually have to break it into 2 parts. What I'm going to do is break up this all the way up to the discontinuity, and then add from that point to the rest of it, right? We're just breaking it up to the things, and then we approach it the same way we would approach it any, I guess, endpoint discontinuity problem, right? We take the limit as, I'm going to use b here. B approaches 1 from the, let's see, approaches from the left, so that of the integral 1 this plus the limit, I'm going to use a in this case, a approaches 1 plus of a 3 dx x minus 1 2 over 3. First off, let me just find the, I guess, the integral of 1 over x minus 1 2 over 3, just to simplify this. So this is side work, some side work right now. Let me scroll a little bit down, just a little bit. So what is this integral here? Well, we kind of have to use like some sort of reverse power rule. You can use substitution, but you can actually do this one in your head, let's see, if I add 1 to negative 2 over 3, I get 1 over 3. In other words, you do the reciprocal, and this is equal to 3, whatever's on the inside, 1 over 3. And you can verify it yourself that if I took the derivative of this, I would get back to what's in the integral. And if you want, you would do u substitution, or you can do it in your head. Yeah. So now we can actually look at this integral. We broke it into 2 parts, and we know what the integral is. So let's just start evaluating it. Oops. So that very first term is the limit as b approaches 1 from the left side of, since I already know the integral here, it's this, precisely this, from 1, or not from 1 anymore. It's, oops, I should have put b here, I forgot. Okay, so there we go. That should be our first part, and then we want to add the limit as a approaches 1 from the positive side of, oops, not the integral since I evaluated it, 3 x minus 1, 1/3 from this to there. So I'm going to scroll down from here, right? Let's just plug in what b is here. We're in 0, so it's 3b minus 1 all to the 1/3 power minus 3 to the 0 minus 1 1/3 power plus 3, let's see, 3 minus 1 to the 1/3 power minus 3a minus 1 to the 1/3 power. And we have, I forgot to add on the limit, so let me just write it tiny here. So now we can just plug in, or evaluate the limit, in fact. So if we were to plug in 1 here, we're pretty much approaching 0, because you can kind of almost direct substitution here. Actually, you can direct substitution here, so we're left with 3 like this. And we can actually, let's see, well, any 1/3, this is the same as the square root of -1, or the cube root of -1, which is -1, so this is 3. This evaluates to 3 because you just multiply -1 times -3 and you get 3. So the second part we just plug in, let's see, so it's 3, 2, 1/3, and then this goes to 0 because a is basically 1. So we're left with plus 3, 2, 1/3. And what is that? Can we just go ahead and write it more nicely? It's equal to 3 plus 3 cube root of 2, and that's the answer. So let's look back at this problem. So I'm gonna scroll out. There we go. Hopefully it's good. So this is the problem. We found that there was a discontinuity somewhere in the middle, so we had to break it down into 2 parts and then treat them like the endpoint problem, where we take the limit from as approaching from the left side and then approaching that same number from the right side. And then I just did side work here just to find the integral because it might get messy if I were to continue this line. And then here it is. Now I just plug in the limits of integration. I get this, and then now I just simply evaluate the limit and we get to our final destination. So this is the idea, and this one's nice because it converges to a number. We can actually say it converges, so converges, especially if the problem's asking if it converges. So now we look back at the definition, just a quick review. Oh, let me just scroll. That's good enough. Remember that when we have endpoint discontinuities, we actually have to, they're actually called improper integrals because you can't actually get exactly at point A. So we actually have to take that technique we learned with the infinite bounds or infinite limits and take the limit and use kind of like a substitution or like an A variable or a B variable to do it. And then case 3 is kind of like case 1 and 2 combined, where we just basically break it up into 2 and then we just treat it as a case 1 and case 2 in this case. So this is for infinite discontinuities, and then there's one more that we're going to talk about for improper integrals. It's just something about comparing integrals together. So as for now, this is the end of this video, and in the next video we're going to probably finish improper integrals. So that's it.